In 1936, a 24-year-old Cambridge mathematician was taking a walk through the meadows when he had an idea that would change the world forever. Alan Turing wasn't thinking about computers, they didn't exist yet. He was thinking about a simple question: can everything be computed? His answer would define the limit of what's possible in our digital age. In this video, we'll explore how a mathematical crisis sparked the entire computer revolution, what a Turing machine actually is, and how every algorithm you've ever used can be simulated by this simple model, and how Turing proved that certain problems are fundamentally unsolvable. At the turn of the 20th century, mathematician David Hilbert posed a bold challenge. Could mathematics be completely mechanized? He believed there should be a definite procedure, an algorithm to determine the truth of any mathematical statement. Three brilliant minds would tackle this question in the 1930s. Kurt Gödel shook mathematics with his incompleteness theorems, proving limits to what can even be proven. Alonzo Church developed lambda calculus, that is, a formal system for computation. And Alan Turing, he invented an entirely different approach, an imaginary machine. In this video, we will look at Turing's approach to this problem. Turing machine is an abstract model of computation. It manipulates symbols on a strip of tape according to a set of rules. What is a tape? A tape is an object which is divided into cells, and each cell houses a symbol from a finite alphabet. The tape is assumed to be extendable arbitrarily to the left and to the right. The machine also contains a head. The head performs several key operations on the tape. It can read and write symbols on the tape and also move the tape left or right, one cell at a time. But how does a machine decide what to do? The machine also has a finite set of states. The machine begins in the start state and continues to run until it reaches the accept state. After each step, the head modifies a particular cell and the machine changes its state. States of a Turing machine change according to rules given in a transition function. Here, we look at a specific example of how such a function acts. So, according to this, if the Turing machine were at state Q0 and it was to see the letter 0, then the header is supposed to rewrite that cell into a 1, move to the right, and also change the state of the Turing machine into Q1. Now, we will see a very common algorithm being implemented using a Turing machine, namely binary addition by 1. So, in the start state of Q0, the head just keeps moving to the right until it reads a blank. That is, it reaches the end of the number. There, the state is changed to Q1 and the head moves to the left. The rules are simple. If the head sees a 1, it changes it to a 0 and moves left. Otherwise, if it sees a 0, it changes it to a 1 and the machine halts. Now, here's the mind-blowing part. Every algorithm we use today, sorting lists, searching databases, running AI models, can all be simulated by a Turing machine. This isn't just about binary addition. Modern programming languages like Python or JavaScript, they're just more convenient ways to express what a Turing machine could do. This is essentially the Church-Turing Thesis. Anything that's algorithmically computable can also be computed by a Turing machine. Now we know that a lot of algorithms can be implemented using a Turing machine. Hence, a fundamental question arises. Does there exist a program that takes an algorithm and string as an input and decide whether this algorithm also loops on that string? This is the essential crux of the halting problem. Turing showed that such a program cannot exist. Now let us look at a simple proof of the above. Suppose it did. Then consider a halting decider as above, which takes an algorithm and a string as input and outputs halt if the algorithm string Otherwise, it outputs. Now, we construct a machine using H and call it D. So, D inputs an algorithm and returns loop if the algorithm halts on itself, and it returns halt if the algorithm loops on itself. So, now the fundamental question becomes, how does D act on itself? Suppose D halted on itself, that is, H of dd is halt, then by construction, D must loop on itself, which is a contradiction. In the other case, where D loops on itself, a similar contradiction arises. Turing's 1936 paper on computable numbers laid the theoretical foundation for computer science before computers even existed. His Turing machine became the standard model for what computation means. Within a decade, physical computers were built, and they were essentially Turing machines made real. Knowing what's impossible is as important as knowing what's possible. Turing's proof didn't discourage computer scientists, it focused them. It led to the theory of computational complexity, cryptography, and the very architecture of modern software. Every time you run a program, you're witnessing Turing's vision: symbols, states, and rules.